We'll rise up from the dust. Oh, here we go, go, go. Let us heal and grow. You won't be alone. We're unstoppable. Don't be afraid to show what we're going for. This is what we know. Here we come back to life. We're still breathing. Standing up, everybody's gonna see it.
And we're back. This is section 3.2, domain and range. The objectives are find the domain of a function defined by an equation and graph piecewise defined functions. So in the previous sections, we were introduced to the concept of domain and range. In this section, we're going to be practicing determining domains and ranges for specific functions. Now keep in mind that in determining domains and ranges, we need to consider what is physically possible or meaningful in a real-world example. We also need to consider what is mathematically permitted. So for example, we cannot include any input value that leads us to take an even root of a negative number. In a function expressed as a formula, we cannot include any input values in the domain that will lead us to divide by 0. We have to keep this in mind. So in this section, we're going to be writing everything in interval notation. I wanted to present a table that shows all the different possibilities for this. So remember, we're going to be using a bracket when the set includes the endpoint and a parenthesis to indicate that the endpoint is either not included or the interval is unbounded, as in infinities or negative infinities. Let us start with two examples here. So I want you to find the domain of the following set. Well, what do we know about ordered pairs? That is right. In an ordered pair, x comma y, x serves as the input and y serves as the output. So if you can see, for the very first ordered pair, -5 is the input and 4 is the output. In the second one, 0, and in the third one, so on and so on. So, what do you think? That's right. We should say that the domain is the set containing the -5 from the first order pair, then the 0 from the second, the 5 from the third, the 10 from the fourth, and the 15 from the last order pair. All these are the values that serve as the input or the domain for this particular representation of a function. What about the second one? F of x is equal to 5 minus x plus x cubed. Now, what type of function is this? That's right, it's a polynomial. What do we know about domains of polynomial? Yes, all real numbers. So how do I write this in interval notation? What is the smallest value in all real numbers? That's right, negative infinity. How far do we go? Positive infinity. Now here's a real challenge. This is a rational function. What is the domain? Yes, I see. We have a numerator and a denominator. And we know that the denominator cannot be equal to 0. So we want to exclude all those values that make the denominator equal to 0. I think we should factor and find out what values for x give me a denominator for 0. Here we go. So we want to find values of x where x squared plus 9x minus 22 is equal to 0. Get ahead of me, factor this. So if you do this, you get the quantity x plus 11 multiplied by x minus 2. Now the zero product property says that this means that x plus 11 is equal to 0 and x minus 2 is equal to 0. So if we solve the first one, we get x is equal to -11, and the second one gives us x is equal to 2. So these are the two values we do not want. So our domain includes every value except x equals -11 and x equals 2. So we need to write this in interval notation, but I think we should take a look at a graph to verify that this is true. So here's a graph of that rational function. Notice that at x is equal to -11, I have a big break, and also where x is equal to 2. That is exactly what we found in terms of values that cannot serve as the input. So the lowest possible value for our domain is, of course, -infinity. And how far do we go before we reach the break? Yes, -11. We do not include the -11. But after negative 11, we can continue all the way up to 2. So I have to unite this with the interval from negative 11 to 2. That's the next break. And then we need to unite this with 2 all the way up to the largest value, which is infinity. And here is my domain for this particular function. Pretty tricky, huh? I have provided some step-by-step directions on how to be able to write these type of domains. Okay, here is one more. Find the domain of the function f of x is equal to the square root of 5 plus 2x. Do we have any restrictions here? Yes, we cannot have negative numbers underneath the square root. So what does that imply? Well, we know that 5 plus 2x must be greater than or equal to 0 because we can't have the square root of 0. Okay, if we solve for x, let me see, I'm going to add negative 5 to both sides. That's going to give me 2x is greater than or equal to negative 5. I'm going to divide both sides by 2, and that's finally going to give me that x must be greater than or equal to negative 5 halves. This will ensure that I only have positive numbers underneath the square root. In an interval notation, this means that I'm going to start at negative 5 halves. And how far do I go? Yes, infinity. Let's take a look at a picture. And here's a graph of that particular function, the square root of 5 plus 2x. Notice that we start at negative 2.5 and we go all the way to positive infinity in the domain. I have also included step-by-step directions here on how to find the domain of functions with an even root.